In lesson 17, we're learning about coefficients. Oh, hold on, I gotta move my screen over here. There we go. We're going to be talking about coefficients. This is really the most important part of the lesson here. It's going to get us ready for something tomorrow. Really today we get introduced to it, dealing with terms. Tomorrow we're going to be learning how to add like terms, and that's pretty important. It's easy to confuse. But to lead into that, we're going to talk about these expressions right here. We would say that these are all, it's multiplication, but these are all factors. In other words, 4 times x times y is an expression where we're multiplying these factors. Factors multiply to get a product. We know that a product is an answer to a multiplication problem. And all of these are ways of saying the exact same thing. 4 times the quantity xy, x times the quantity 4y, y times the quantity 4x, and you guys can see that those are all the same thing. What we want to talk about though is that each of these really technically can be a coefficient. A coefficient is a part of that expression. But for our purposes, we, in our book, are not really going to worry about x's and y's being coefficients, although they technically can be. We're only worried about numerical coefficients. So the way that we would usually write this, all of these, is 4xy, with 4 being the coefficient. We don't even really say it's the numerical coefficient, although it is, because it's a number, not a variable or an unknown like x and y. But we would call this just the coefficient. 4 is the coefficient, and what it does is it tells us how many xy's we have. So if we had 3a, a is considered the coefficient. It tells us how many a's we have. If we had negative 4b, we can have a negative coefficient. It tells us how many b's we have. We could have 1/2 a, b, c. 1/2 would be considered the coefficient. It tells us how many a, b, c's we have. So we throw out the word numerical, and we just talk about coefficients as always being numerical. So your book gives a couple examples: 4xy, negative 15 pq, and 81 xmz. Here are 3 examples, and what we're going to learn tomorrow is how if we can combine these. So the coefficient would be 4, tells us how many xy's I have. Coefficient would be negative 15, tells us how many pq's I have. The coefficient would be 81, tells us how many xmz's I have. Next we'll talk about terms. These are the terms examples listed in your book. Terms consist of a single variable or constant. They list 1, 2, and 3 in your book. It says a term is an algebraic expression that consists of a single variable or constant, is the indicated product or quotient of variables and or constants, and 3 is the indicated product or quotient of expressions that contain variables and or constants. I think it's easier just to look at them and say a term is basically something that can simplify to one value or one number. And so 4 obviously simplifies to 4. It represents 4. X, if we were given a value for x, it could represent 2, 3, 4, 1/2. It could represent pi. But let's say it represents 3. 4x, if x were 2, this value would simplify to one value, 8. We could have all of these values given to us. What is x, what is y, what is a, what is b, what is p, and maybe this simplifies to 1/2. So it can be a fraction, but it's still going to simplify to one value. And the same here. This would simplify to one value if somebody told us what x and y and m were. So if we had a long expression, this is what we're going to run into tomorrow. So if we had 4x plus 2ab plus 9x minus 2a minus 4 plus 6y. So here's this big long expression. And you might say, well, technically can't all of these, if we were given all of these values, couldn't we then simplify it to one big value? There could be an answer to this, in other words. And although that's true, that's not really the way we define terms. The way we would mark these terms, change colors here, is we would say, okay, 4x is a term. Positive 2ab, I take the sign with it. 9x is a term, but it's a positive 9x, so I take the sign with it when I consider what term it is. 2a is a term, but I take the sign with it. It's really negative 2a. Negative 4 and positive 6y. So in this particular expression that we started with, I have 1, 2, 3, 4, 5, 6 terms. The coefficients of each term, I have a coefficient of 4. I have a coefficient of positive 2. I have positive 2 ABs. I have a coefficient of positive 9. I have 9 X's. I have a coefficient of negative 2 in this term, negative 2 A's. Just have a value of negative 4 here, and a coefficient of positive 6 here, positive 6 Y's. So I've got 6 terms in that expression with a bunch of coefficients. And tomorrow we'll learn how we can determine if we can add any of these together or not. So one way of looking at it is coefficients are divided, or sorry, terms, you'll recognize them by addition and subtraction signs. So if I had 2a plus 3b minus 6y, my terms are going to be broken up by addition and subtraction symbols, not the multiplication, but addition and subtraction. I've got a term, I've got a term, and I've got a term. The last part of our lesson deals with the distributive property. It's the idea that we can distribute a value through a set of parentheses, and it's going to help us to eliminate the parentheses. We're going to get rid of them because a lot of times we want to get rid of parentheses. So we have a times the quantity b plus c. I can distribute the a through because every term, we talked about terms, there's b plus c. There's 2 terms in here, a b and a positive c. Every term in here inside the parentheses gets multiplied by whatever is sitting outside to distribute through. So in this case it's a. So we would have a times b and then a times c, and you get ab plus ac, because a times b is ab and then a times c is ac. And we can have as many terms as we want inside of the set of parentheses. Here we have 3 terms, a positive b, a positive c, and a positive d. So if we were to simplify this and distribute the a through, we'd have ab plus ac plus ad. Does not matter how many terms are in those parentheses. Every term needs to get multiplied by a. And there is value in eliminating the parentheses. We might say we've made it more complicated, but there'll be a value later on in eliminating these parentheses. So if we apply to numbers, we could take 2 times the quantity 3 plus 4. Now the old way of doing this, nothing wrong with doing it this way. In fact, in this particular problem I think it's probably easier. But you would say, okay, let's follow order of operations and say 3 plus 7 is, or 3 plus 4 is 7, so we'd have 2 times 7. That equals 14. And now with the distributive property, we might say, well, I'm not going to simplify 3 plus 4. I'm going to distribute this through and say 2 times 3 is 6 plus 2 times 4 is 8. The answer is 14. We get the exact same answer regardless of how we do it. But sometimes we don't have values. Sometimes we have 2 times the quantity A plus 4. And so we don't know what A is, but we do want to get rid of the parentheses. We distribute it through and say this is 2A plus 8. One of the real values in the distributive property is mental math. I just want to mention this. We use it all the time without even realizing we're using it. If we were to go to the store and find shirts on clearance, really cheap shirt, $1.99, and we really like the style, so in fact we're going to buy 3 shirts that are the different colors, and if they're $1.99 each, we'll just pretend there's no sales tax. Most of us do not take $1.99 times 3 to figure out how much the shirts are going to cost, because we're in a store. We'd probably need a pencil and a paper to figure out, all right, 27, and carry the 2 over here, and it would take us, it'd probably be too challenging to do mentally. And so we take a shortcut and we use the distributive property. We say that $1.99 is the exact same thing as 200 cents minus 1 cent. And again, most of us aren't even aware that this is what we're doing. We're using the distributive property. And we're saying I'm going to buy 3 shirts. And so I'm going to distribute the 3 through and say I know if I bought 3 shirts at $2 each, they would be $6 or 600 cents. And I know that it's not quite actually $2. For each shirt, it's going to be 1 cent off. So I'm really distributing that 3 through, and I'm saying it's 600 cents minus 3 cents, or 597 cents, $5.97. We do this all the time in mental math, and it wouldn't matter if this was a subtraction. Maybe this shirt was $2.02. That'd be a little easier to do mentally. You probably actually could pull that off because there isn't a lot to carry. But even still, most of us, without realizing it, we say, oh, 202 cents is the same thing as 200 cents plus 2 cents. And we distribute the 3 through. $6.06. So the distributive property is very helpful with mental math. The last thing we'll do with the distributive property here is just take a couple expressions, multiply them through. If I had the quantity mn times the quantity x plus y plus 2p, I would distribute mn through every term. Here's a term, positive y is a term, positive 2p is a term. So I distribute it through. So this becomes mnx plus mny plus 2pmn. Here we have the quantity x minus 3y plus xz times mp. I'd probably take this mp and rewrite it and put it over here, just because I like having the value that I'm distributing through on the left side, but it doesn't matter because this is multiplication and multiplication is commutative. We can leave it over here and work backwards, but I am going to go all the way over to the first term first here. I'm going to go all the way over to x. So it's mpx, and then here the term is negative 3y. This negative sign goes with this term. So this becomes negative 3y mp, and then finally plus mpx z. I could have wrote it x, z, mp. Doesn't matter. It's all multiplication. It's the same. So we distribute that through.